bus station. Okay, so there is a bus station, and the time is the time for a customer to arrive at the bus station. Okay, so customer go to the bus station. And so this is the arrival time of the first customer at the bus station. And this time is the time that second customer arrived at the bus station, etc. Okay, so that and because that customer arrived at a bus station randomly, you cannot predict, right, in a normal situation. So you have the point. So you mark a point on the time axis, so that you have a point process. Okay, so you have time, random time here, and you have to notice that the random time is ordered. And you cannot exclude the possibility. I mean, the case that two customers arrive at the same time. Okay, at the same time. But we will see that in our model, the probability that the probability that two customers arrive at the same time, right, is 0. I mean, in most sensible situations. But in principle, you have to make that equality here, okay? Because in principle, it's possible you have to, even though the probability for that event to happen is 0. Okay? So that is 1, is 3, etc. Okay, so that a point process actually is a sequence of random times. So actually, you have a sequence x1, x2, etc. And every value of the random time is non-negative. So that is very simple, right? The description is very simple. Okay. And what we observe here is an outcome. So I indicate omega here. Okay. So for a certain outcome, omega, we know that the first arrival is here, the arrival time is here. And the second order comes here, etc. Like that. And then you can ask, for example, you ask that how many arrivals, how many points, or how many time points you have between time 1 and time 2. You may ask this event, right? How many, all right? So you can record. And so the number of points from T1 to T2 will be a random value, right? It's a random variable. And this random variable is a function of this point process. Okay? A function of this point process. So you may ask a lot of meaningful questions. So let's see, so for example, in the study of Poisson process or the study of point process, the waiting times are time at which events. So we said that some event happened, but please don't confuse the events here to the event we defined because we say that in the probability space we have a sigma algebra F consisting of all events of interest. So that is the event. In that situation, the event is just a subset of the sample space. Okay. But here, the event here is just a traditional meaning, means that something happened. For example, customer arrived at the bus station. It's an event. Or a customer arrived at a bank. Okay, it's a certain event. Or you can say accident happened in the highway. Okay, so for example, if you record the accident happened in the highway number 1, then then you record the time that an accident happened. So for example, starting from the midnight, that's time 0, and then every time when there is an accident happened, you mark the time. Okay, and so accident becomes to a certain kind of event. So that's why I use a double quotes to signal you that the meaning here, even though the English word is the same, but the context is different. Okay? So this is an example in a post office, customer coming for service or event. Each time a customer comes for service, then an event happens. So that okay, so this is very common because that in everyday life you have such kind of description about point process. Okay. So point process is very important in traffic. Like if you are studying the traffic in a mobile station, because we know that the the mobile network consists of many different access points, the base stations there. So each base station can have a high capacity to serve the customers. Okay, and so if you want to study how crowded that the base station is, then you have to study the arrival pattern of the customer. And for sure, if a base station is located in a metropolitan area, like in a 101 high building in Taipei City, then there are a lot of tourists, and so that this should be very crowded. But if there is a base station in the high mountain area, then you can observe, you can conceive that not so many customers, right, for service, right? So the pattern of the traffic will be different. Similarly, you can study the traffic in the highway. For example, in the period of Double 10 festival, you will know that there are a lot of cars driving on the highway. But in normal time, I mean, in weekdays, that most of the time the freeway is not so crowded, so that the traffic pattern will be different. And so you will have a different point process to discuss. All right, so that this is a point process. Okay. So now let me see. Okay, here. So now so consider a point process. So this is the point process. Then we can define a new process, associated process. Okay, n of t, right? N of t, and it's an integer value. So it means that each random value is for each t. Now t is continuous time. For a point process, the index n is so it's just the index for the order, right, of the arrival of certain type of events. But here n of t is continuous. And for each t, n of t is an integer value, the stochastic process. And we defined that n of t greater than or equal to n if and only if. So here is a number here. Suppose that t is equal to t1. Okay. What is n of t? N of t is the number of the points of the random time, right? Less than or equal to t. So if t is equal to t1, then nt omega. So for this case, so n t1 omega. For this outcome, at time t1, what is nt1? 1, 2, 3, right? Because before, so this is 3. And n2 at time 2 here, okay, for this outcome omega, the number of points, alright, before our equal or on the time t2 is 5. Okay? For this particular omega here. So this n is called the counting process because we count the number of time points. Okay, the number of time points before our on the specific time t. Okay, so this is the for every point process, right? Sn, there is counting process associated with that point process here. So the definition and the description here is very good. That the number of points before our on t is greater than or equal to n, so it's an event. It's an event. So this event is equal to the event that the nth arrival time is less than or equal to t. Because if the nth arrival time is less than or equal to t, it means that there are at least n points, right, before our on t. Right. So this event is the same as this event. It's very important to notice that. Okay. Right. So now this is the expression, the explanation that the counting process NT represents the total number of events that have occurred up to time t. So this is what I have done here. Any questions about the definition? So every point process has an associated counting process. Okay, so they are two viewpoints of the same thing. Right? Two viewpoints. Okay, now, so sometimes we use the counting process. So for a counting process here, so we know that that the value is always negative because we count the number of points. So the number will be negative. Of course, it's integer value. Second and third thing is that if h is less than or equal to t, of course, the number of points up to time h will be less than or equal to the number of points up to time t, because t is longer than this. Right? So of course you have this. Okay. And the difference. So if s is less than t, just like here, so what t1 is less than t2, right? Okay. And so the difference is the number of events occurring in here. Notice that not include the time point s, because that nx means the number of events arrived up to time s, including the exact time at s. So the difference here is the number of events occurring in this up, open, and up process. Alright, now to use counting process or to use point process to model certain random phenomena like the traffic in a highway or the customer service in the post office or in a bank. Right, or in a bus station, that we always assume certain additional properties. Okay. And so the first one is called independent increments. Now I explain that if I have a time t1, t2, t3, tn minus 1 up to tn, but I have n times. With this order, okay, and now nt1 is the number of points, right, up to time t1. nt2 minus nt1 is the number of points in this hot open hot close interval, right? And NT3 minus NT2 is the number of points in this interval, etc. Okay? Right, so we have, we call this increments, right? This is called increments. Increments here. And so if all such increments are statistically independent, because each increment is a random variable. Okay, so we have here we have n random variables here, and if these n random variables are statistically independent, then this counting process is said to have independent increments. Right, and in many linear phenomena, the assumption of independent increments is quite reasonable. For example, if we are discussing the service in the post office, the customers are from around the area. So the customers, they may not have any relationship to each other. Okay, so they come to the post office for service at random. So that it's quite reasonable to assume that the point process as a model for the service in a post office has independent increments. Okay, right? So now, so this is the situation to have independent increments. The second is the stationary increment. Right? So so that for any so suppose that the okay, so t plus s1, this was S1 and the S1 plus t, right? The time interval has length t. Now from S2 to S2 plus t, this interval is length t, etc. And S3 plus t, this interval is length t. So we have three intervals, alright? All of them has length t. And in many situations, we will assume that these three intervals has increments. They are identically distributed. So they have the same distribution. Okay? They have the same distribution. If the behavior of the traffic is stationary, stationary means time stationary. For longer time, they are stationary. So this is assumption. When you make this assumption, you have to realize that in many practical situations, this may not be true. For example, suppose that you are considering the service at post office. The post office has office time, right? For example, the office may open at 9 o'clock in the morning, but close at 6 o'clock in the afternoon. Now, do you think you have any customer arrive at the night time? For example, 8 o'clock. For example, 8 p.m. The post office is closed. Of course, there is no customer, right? So that even though so there is no customer, so that if the time is so late, for example, if this time interval is just at the night time, then I'm so sure you have no customer to arrive at the post office. Okay, so the behavior, the behavior of the arriving pattern of customer must be different. Okay, in the daytime. Right. So of course that if the time interval you studied, or also including the day and the night, then of course you don't have stationary increments, of course. The second thing is that even though in the daytime, because in daytime, usually you have a recess time at noon. For example, you have lunch time from say from 12 o'clock to 1 p.m. Okay, and the arrival pattern within that 1 hour from the noon until 1 p.m. Well, depends on the location of the post office. For example, if the post office is in some area which has a lot of offices for different companies or government agencies, then that as you know, all these curves will go to the post office for service, right? Because in the work time, they come, right? Because the boss will not allow this curve to go out for personal business, right? So all these personnel will go to post office during the recess time. So you can think about that. The post office will be quite busy at the time between 12 o'clock to 1 p.m. But if the post office is in a residential area, no such kind of pattern happened, right? So that so you may probably maybe all the household wives or husbands, they maybe stay at home to cook for themselves or for their family. So maybe they are busy at home and no time to go to the post office, right? So for stationarity increments, that you have to look for the situation you study. Okay. But if you are studying the arrival patterns during the work time, for example, from 9 a.m. to 12 o'clock, within 3 hours, possibly the traffic pattern or the arrival pattern will be very stationary, because there are no such kind of rush hour or anything, right? So you have some kind of homogeneity, and then the situation in that time period from 9 a.m. to 12 noon, that in this period the traffic pattern or the service pattern will be stationary. So you can propose the stationary increments in that time period. Right? So stationary increments give us a lot of convenience for analysis. Right? So the meaning is that if the increments for intervals with the same length, then they are identically distributed. This is the assumption of the stationary increments. Okay? Right. So now we give a definition about the point process. A counting process is called a point process with rate lambda. Okay, so there's a rate lambda. Of course, the rate is positive. If occurs at time zero, there is no event, nothing happened. So that we square b1. Okay, so the counting starts at time zero. At the time zero, the number of arrivals is 0. This is quite reasonable, right? We square b1. And the counting process has independent increments. Okay, so it has independent increments. Right. And the third assumption is that the counting process has stationary increments, because that you can see that this increment, right, has distribution dependent on t. What is t? T is the length from s to t plus s, right, of the interval. So the distribution is independent of s. So from this formula, you can see that this counting process has a stationary increments. And the distribution of each increment is Poisson distribution. And the parameter is lambda times t. Because Poisson distribution has one parameter, and here the parameter is lambda times t. So that the Poisson distribution depends on the rate lambda as well as the length of the interval. I think that's reasonable, right? If the length of the interval is bigger, okay, it is bigger, then you have more time, right? More time points, right, occurs within this interval, and so the parameter is bigger, okay, for the Poisson distribution. All right, so this is the situation here. As we know that Poisson distribution, for Poisson distribution with parameter number t, the mean is also equal to number t. Right? This is a phenomenon of Poisson distribution. Let me ask you, if you don't know the Poisson distribution, please raise your hand. Okay, good. So all of you know what is a Poisson distribution. That's great. So that the lambda t actually is the mean of this increments. All right. And when s equal to 0, n0 is 0 is going to be 1, right? So you can omit it. So this is nt, right? So nt equal to n has this distribution. The probability of nt equal to n is the same as here. Okay, so now we know what is a Poisson process. A Poisson process is a counting process, right? It's a counting process such that 1, 2, and 3. It has 3 properties like this one. Okay, so you start at 0, and it has independent increments, and it has stationary increments, and the distribution of each increment is Poisson, is parameter lambda times t. So that is the basic definition. Any questions? Okay. So how come we have Poisson distribution? Actually, Poisson distribution comes from this identity. We know that the exponential function has a convergent Taylor series expansion, right? So that is the Taylor series expansion, and this series converges for every t. Okay, for every t. So that when we divide both sides by this quantity, right, we have 1, right? So this is total probability, and that this becomes true distribution. Right? So that tells you the origin of Poisson distribution. It's so simple because it's from this identity. Everybody knows that, right? Okay, and the remark I have already said that NT has stationary increments, and the increments has the same distribution as NT. Okay? As I have indicated that this is 0 to b. Okay, so now the first theorem. The first theorem is that if we want to identify, if we want to model the point process has a counting process, which is a Poisson process, we have to check 1 to 3. To check 1 to 3, of course, this is easy, right? The second one is also easy because the independent increments is in many situations so reasonable. The third one to have a stationary increment will depends on the situation you want to study. As I just told you the scenario, you have to clarify that. Which time intervals you want to study. Right? At nighttime, daytime, in the morning, afternoon, or just in the lunchtime. So you have to clarify what time interval, what time period you want to study. All right, and if you limited the time interval you study, quite often you have a station increments assumption. But the tough thing is that is the distribution of the increments. The sum distributed. That is a good question for you to test, right? Right. So you have to test whether the increments has such a distribution. Okay. And in many situations, this is not so easy. So we will have a theorem here. And it says that a counting process, a Poisson process, means that a counting process has these three properties. Right? If and only we have four properties. Right? The first one will be identical to this one. As I say, this is easy, right? And the second one is that the counting process has independent increment and as well as station increments. That can be, you can have an argument, right? You can argue for that. But and then it avoids with the third and the fourth properties that these two properties give us this distribution. And you can think about, you can see that these two properties are much more easier to check. Okay, so it says that, especially for little h, when we say little o, means that this identity, this equality, right? This equality means that when h is so very small, the little o means that this term will be smaller than h. Right? Little o means something smaller than h. Right? Here this definition, I think you know the small o, right? In calculus. A function is called a little o function, right? As OS. If this is true, means that as x goes to 0, the function value decay to 0 faster than x. For example, x squared. The square of x decay to 0 faster than x decay to 0, right? So x squared is a little o function. Okay? So example is fx equals x squared. So limit you check, right? So you can check because that you don't allow negative x, right? Because in the square roots under the square root don't. So I use this one. So this is the limit. And this is called infinity. So the square of x goes to 0, much slower than x. Okay? And so that at the extreme, the ratio becomes to infinity. It's amazing. Okay, so that so theta O means that as h is quite small, this term is smaller than h. Right? So that approximately, if h is very small, the probability that this event will occur is almost equal to lambda times h. Okay? So that when h is quite small, the number of points occur within such a small interval. One, there's only one arrival, would be lambda times h. And you have more than one, means that you have a number of arrivals greater than equal to 2. This event to occur with very, very small probability. That is very reasonable, right? Because that if the arrival pattern, for example, if you study traffic in the freeway, and you consider a microsecond, right? A microsecond, very, very short time interval, and there is a car goes through, come to the some service station within 1 millisecond. I think one car to occur will be rare, right? So you have two cars to occur within 1 millisecond will be unusual. So the probability for that event to occur will be very, very small. So that is the situation. So with third and fourth properties, that you can very easy to identify the situation. What kind of pattern, what kind of trajectory pattern satisfy 3 and 4. If 3 and 4 can be satisfied, then in the coming process becomes a sum process. So you have a theorem that for you to identify the fixed trajectory pattern of which point process can be modeled by the Poisson process. And of course, as I just explained, that many practical situations you have 3 and 4. It's quite reasonable to have that. And from that, you can find out the h, the rate, because that the rate becomes to, so that lambda becomes to divided by h. Okay? So that the rate can be computed by what? By the ratio, the probability that there is one arrival in a very short time interval h, with length h divided by h. Okay, so you can do the measurement many times and find out this probability, right? And divide by h. And as h goes to 0, then we find out the rate now. Okay, so you can get the lambda here. So once you get the lambda here, then you know the distribution, right? You know distribution. Because you know the Poisson distribution with parameter number times 2. So that is the so this theorem is very important. It's giving you an easy way to check whether the coming process is Poisson process. Any questions? Okay, and the proof. So I think I have to stop here. So I put that on Friday.